now we need to build our material from here as to what is the signal, right? We see this, the net magnetization is in that direction, and that the strength of it, we need to relate it to some of the variables that we have been talking about. So let's take a small sample volume. For explanation, it's a nice cuboid that we have taken, which is not that different. I mean, your images, if you actually recall, in the images we call about pixel, it's always some square or rectangle. When you go in volume, you're going to have volume element. So we are taking a sample volume which is a cuboid here, and when you subject that volume to the external magnetic field B0, the static magnetic field, then there is a net magnetization M, that is along the direction of B0. So at equilibrium, what do we mean by equilibrium? You take this sample volume, put it in the external magnetic field. Initially, each of the nuclei are all in different random directions. So give it some time, right? After you give it some time, every nuclei is trying to align to, if it is a hydrogen, it is trying to align to its up preference at 54 degrees. There are more of them, or it is going to be 180 minus 54 the other direction, but then there are more on the up direction. So you have a net magnetization after you leave. This is called as M0, which is the equilibrium value. So that is the net magnetization at equilibrium from that sample. Okay. Of course, that depends on X, Y, Z, meaning that depends on the volume itself, where you are picking, how many nuclei are there inside that volume, right? So if I take a different volume, then I might get a different M, because that may have a different number of hydrogen nuclei. So depending on the volume which you pick from the XYZ, the amount of signal that is there, or amount of M, or amount of equilibrium M0 that you are going to get is going to be different. So the magnitude of this magnetization vector is given by this formula right here, and you will notice that there are several constants, known constants, so which we don't have to worry about. So Boltzmann constant, temperature, T is okay, it's all body temperature, so we assume that the material that we are taking, the sample that we are taking, is in body temperature. So T is not a problem. K, the Boltzmann constant, is not a problem. These are universal constants, right? K. So what are we left? And then there is a H, which is the Planck's constant. So again, that we don't have to worry about. We don't have much control. It's universal constants. So what do you now have? You have the magnetization vector M0, which is at equilibrium, is actually dependent on B0, which is the field strength of the static magnetic field, and then proportional to gyromagnetic ratio, square of the gyromagnetic ratio. What is that gyromagnetic ratio? It is a material property. So if I choose my material, if I say I am interested in hydrogen, then the gamma is same, right? How do I know it is hydrogen? If it is gamma, then I know the signature frequency. So if I get signal at that frequency, then, which was 42 point whatever for 1 Tesla, right? So depending on B0 that you are using, you may have gamma, the megahertz. So your gamma is for hydrogen. So that also is not a problem for me. So your net signal that you are getting is directly proportional to PD. What is PD? Proton density. What do we mean by protons? So positively charged protons. So in case of hydrogen atom, you have only one proton. So in that sense, it is technically called as proton density, but in our case, we are doing hydrogen, so they loosely use. They say proton density, and it is given that for biomedical, we are mostly interested in hydrogen. So you have to be careful in the jargons when people use. So proton density is strictly proton density, but that is positively charged. How many protons are there in that volume? But in our case, or in biomedical MRI, mostly first importance is hydrogen, right? It's somewhat not said, but it is essentially amount of hydrogen nuclei that is there, the density. So that is your M0. So essentially what we are now getting towards is, you take a sample volume, if you can measure M0, you can see that if you choose a magnet, so B0 is chosen, gamma frequency you are tailoring it to hydrogen. So the signal strength that you are getting is corresponding to the hydrogen frequency. Then The m naught is directly proportional to only the number of protons. So if I choose my sample same from different locations, if a sample has more PD, then it will have more signal. If a location has less water content, less hydrogen, therefore that will have less signal. So I'll have more signal or less signal dependent on your PD. This is the fundamental signal that we are talking about. I wouldn't say signal as yet, because this is the physics, this is the quantity that we are going after. How do we record and what is the signal? We already spoke initially, right? We have to record this magnetization. If you have magnetic vector that is looping, then I can actually get a current, put a coil, get a current that will be proportional to this. So we'll get to the details, but essentially this is the signal origin that we are talking about. So just to complete the idea about definition of this Larmor frequency, the spins precess at a single frequency omega naught. But notice, I mean, this is another very easy to state concept but difficult to comprehend. They are not in phase, so that the sum of xy component is 0 with the net magnetization vector in z direction. I mean, that is very complicated to understand. Imagine this is what we are doing. What do we mean by the statement that is made there of not in phase? So let's imagine that each of you are sitting in a class, each of you has, this is your micro spin, right? So I'm saying now all of you to spin, so each of you are going to do this. Of course, if I don't say anything further, each of you, some will be doing it here, some will be doing it there, some will be doing it here. Most people who are lazy will have a hand down. They will do it here in whichever direction they were actually sitting, hand resting, they will do it, right? So essentially, initially it is random nuclear spins direction. That is how it is. Each one is a microscopic magnetization vector in different directions. But pretend now I am subjecting this to external magnetic field, right? And let's say that is my voice command saying, oh, everybody align the spin in the direction going from floor to roof. So the moment I say that, each of you are going to, so each one are initially at a different direction. So net vector is 0. But now I have instructed you to all align along the direction going from floor to roof. This is akin to applying a external magnetic field that is in the plus z direction. So what is going to happen? Each of you are trying to, whichever starting position you had, you have to try to make a attempt to come here. But when you come here, you are not going to align. You are going to precess around. So now notice, of course, some of you will go down, right, and then do it. But the nature of things is, most of you will obey the command. That means the nature says that most people will go to the up state than the down state. So there is going to be net positive, right? So now notice carefully what has happened. Because of the external magnetic field that is applied, or I said in this analogy, I said, oh, everybody align yourself in the vertical direction. You have tried to come and you are spinning. And there is going to be net magnetization in this direction. But when you are spinning around this direction, which is called as, at some frequency, which is called as Larmor frequency. Given that you all are supposed to behave same, you are all hydrogen, right? So that means no matter what happens, after some time is given, right? After some time is given, after the external magnetic field is applied, after some time is given, after it asked you to come here, eventually, right? Everybody would have come doing this. Although you will start, so now I am saying, okay, you are doing this, you all are same nuclei, hydrogen, so you are all doing the same frequency, right? You are all spinning at the same speed, angular velocity. You are doing it very, but now I say stop. That is, I switch off the external magnetic field, or in some sense I say stop. What happens instantaneously? Each of you, if you stop, you will notice, even though all of you are at the same angle, in this up direction, you are stopping. You will notice with respect to the vertical angle, some would have stopped here, some would have stopped here, some would have stopped here, some would have stopped there. So the angle of inclination is same, because you are all hydrogen and you have the resting state that you have achieved at equilibrium. But then when I say stop, even though you're doing this, when you stop, you might be at different positions, right? The angle could be same, but you might have stopped when in the other directions you are at different locations. Some will be in the some will be horizontal, some can be in the the other direction, the x direction, some could be in xy direction. So what is happening? That means you're all supposed to be not in phase. This is what is meant by not in phase. So I mean, I'm going to get into that little more detail, but from here, if you actually position yourself and use all the knowledge that you have accumulated from mathematics and physics, you could immediately guess, oh, I have a net magnetization vector. He is talking about 3D, z direction, x direction, y direction. If net magnetization is there in z direction, because all of you are trying to come, or most of you are here in this direction, and therefore there is going to be a net magnetization in the z direction. No problem with that. But if you are in different phase, what does that mean? That means if I project each of you on the xy plane, the xy plane, the directions can be all through 0 to 360, right? Wherever you stopped. So that means in the floor, if you sum all the vector components in the xy direction, the magnetization components in the xy direction, I don't have any signal, because it will again be in all directions, so it will all sum to 0. So now you understand that when we talk about magnetization vector, there is a net magnetization vector in the z direction, but if you are in all different phases, that is, if you don't make an extra effort, then there is still randomness in the xy direction, and therefore the component along the xy plane will go to 0, right? So let's put some images to explain. So this is what it is. The blue color arrow mark that you see is the external magnetic field, right? So each one is spinning at different orientations. When you apply the external magnetic field, they all try to align, and these are the relate this to the different hands where each would have stopped. So these are it's spinning around, and there is a mz. So now this might make sense how to make the spins in phase. Now that you understood what do we mean by in phase, each one is, there is a net magnetization in this direction, but each one of you are stopping, right? Each one depending on where you started obeying the command, you would have joined the precision at different locations. So there is going to be different orientations that you're going to, if you start little later than the neighbor, you will continue to be that same amount late every time, right? So how do we make this in phase, right? That is a next level of engineering that we need to talk about. So we can make this happen if I'm able to communicate and say, that means in this case, if I can communicate, create another magnetic field that can actually talk with or have influence with this spinning at the same frequency, right? So relate to your regular forces that we the gravitational field, what we can do. You have something like this. If I'm moving, right, how do I push this fellow to, if it is doing this, how will I push this to ground? Oh, I have to push to ground, but then if I just have a force like this, then I will only hit one time. This will go here, this will go, then next time he comes, he'll go here, then he'll come. So if I have to push him down, what I need to do is, I have to move with this guy, push him down and move with this guy. I have to push him down, move with this guy, push him down, move with this guy, push him down. That means I have to move with this guy. If I have to move with this guy, I have to have the same frequency, right? Here, that means if I have to apply external magnetic field, I have to apply the external magnetic field at the same frequency of the Larmor frequency of this guy in the other direction. So now, not only you have the external magnetic field that was static, where you had net magnetization in the z direction. Now I am applying another magnetic field, which is B, which is rotating, okay, subjecting to rotating magnetic field, and that means it has a frequency of omega naught, which has to be So it has to, in this analogy, right? It has to move at the same velocity. So your angular frequency omega naught should be exactly same as your Lamar frequency of what you are doing. If you do that, then given some time, all of you are going to have hands. So now, wherever you started, if I give another command and say, no, you go slow, you go fast, but next 2 seconds, all of you make sure that your magnetic spin is in front of your nose, right? Just to make it interesting. So wherever you would have started, you would make that extra effort to bring it there, and from there on, all of your hands will spin with not only the same angular frequency but also same phase. So if I take one instance, then I will not see several vectors. I will see only one hand because everything else will be synchronized. Okay, so just go back to our previous process involved. We have covered this step. Put the patient in static field. So you know what happens now. Put it in static field. All your microscopic magnetization start to align. Give a net magnetization in the z direction. So wait until nuclear magnetization reaches an equilibrium, right? That we talked about. Now there is a net magnetization in this direction. But how do I measure it? That is the next level of engineering that we need to do. How do I measure this? So in order to measure this, the first step I'm trying to make is I will apply another rotating magnetic field so that I can bring this component in the XY direction. Okay. So M of t precesses around B naught, Lamar frequency, the Z direction. Now you have a component in the Z direction which is referred to as longitudinal relaxation. So of course, just to complete the point, if I now say remove the external magnetic field, right? Now I say, oh okay, you all relax. What will you do? You'll go to your resting state, wherever it was. So that means if I remove the external magnetic field after I make you all obey the command, if I remove the command, how fast you will go to your native state is a characteristic of you, right? Some may go immediately, some may go low, so some may go slow, some may go immediately, some may take their own sweet time, some may not go. Well, let's not take that case here. But the point is, you are trying to relax, right? So you are going to take some time to relax, and given that we have made our components in the XYZ direction, the component in the Z direction, so you're all forced to go up, right? What will happen if you have to relax? If you have to relax, you're going to go to 0, right? So when I start, I have coherent signal. The component in Z direction increases in time with longitudinal relaxation. Why? Because your B naught is still there. Your static field is there. The component in XY reduces with time. That is, you're becoming out of phase. Right? Each of you are trying to go back, so each of you will are out of phase. So measure the transverse component at certain time after excitation of NMR, you get the NMR signal. That is, you have in the static magnetic field is always there, so you have always the Z naught, right? But then I have moved the Z naught, pushed this Z naught into the floor, and I have given another command so that they are in phase. So I have made this magnetization vector. Initially it is 0 in the XY plane. I have given another rotating magnetic field, made everything coherent, and I have pushed the value to the XY plane. Now if I remove that external rotating magnetic field, it will start to relax. That means it will start to dephase. So your component in the transverse plane is going to go to 0, but it is going to try align itself to the external magnetic field. So your Z component will go up. That is what they mean by relaxation. Okay, we go into this again and again. And this is the whole crux of the story. So now you do this again and again, you get multiple times. That's the signal. So now we have come until understanding what is the magnetic vector, signal, magnetization vector, and we have come to the level of understanding that we could manipulate this M so that you could get longitudinal signal. I mean, you have the magnetization vector in the XY direction or in the Z direction. That much we have understood. And of course, the speed with which it relaxes, right? When you remove the excitation, has to be a material property. So that is one is proton density we saw. How fast it dephases is one time signal, which is T2 they call, and how fast it comes back to equilibrium after the excitation is removed is another time constant, which is T1. I'm sure you would have heard T1, T2 weighted MR images. This is our fun. We'll understand exactly what is meant by